Hello everyone, welcome back to ptet.chemistry channel. So finally we have arrived at the 10th out of the 10 video series on these infographics provided by Cambridge International on their Resource Plus website during the worst of the pandemic back in March or April. So to get a copy of these PDF, you can just look down at the video description information. There is a link to a Google Drive file. There's the PDF of this infographic that I'm going through today. If you are here for chemistry tutorials for your paper 2 or whatever theory paper that you'll be having, this is not really a chemistry tutorial video. It's more of a topic connection kind of video. So if you don't enjoy that kind of thing, if you know what you're here for, then by all means skip this video and go straight to the other playlist on my channel, either the topical chemistry playlist for A-level chemistry, or you can go through the component paper tutorials for those of you who are doing the Cambridge International. Okay, but I mean for those who are not doing the Cambridge International, the topical playlist will be useful to you regardless, because they've been sorted out in topics such that irrespective of whatever point in your curriculum, whether you're doing EDEXL or AQA or WJEC or the Scottish A-levels, or even the Australian HSC, the High School Certificate Exam, or the New Zealand NCEA, I think, or wherever you are in the world really. I mean, 16 to 18 years old British A-level curriculum would be relevant to you if you are 16 to 18 years old and studying chemistry in school, okay? Preparing you for university level kind of chemistry. So this is a much shorter video than the last one, which was on organic chemistry, and that was terribly long. It's because that covers the whole A2 level of organic chemistry. This is about analysis. So in the topical playlist, you can look for analytical methods or analytical techniques, which cover NMR, nuclear magnetic resonance, which cover the proton NMR and carbon-13 NMR. We talk about mass spec. So very soon I'll start talking more on mass spec, which will be relevant to those doing the I think the new UK A-level chemistry syllabus has started talking more about ESI and EI, which is electron spread ionization or electron ionization, which will give you those different stuff, and they are expected to know more about the techniques behind them, which involve the time of flight, etc., etc. But Cambridge International for now only does very simple mass spec, which involve analyzing the final mass spectrum, which is quite a common thing for like ages and ages, decades and decades already. Not just for Cambridge International, but for a lot of A-level syllabus. Yeah. In terms of analysis, we also talk about chromatography. There's like separation techniques, so we can talk about GC, gas chromatography, or liquid chromatography, or high performance liquid chromatography. Those are some of the things you have done in school. There's also a simple stuff, which is thin layer chromatography. That's just done on a silica plate. So dependent on what is your stationary phase, what is your mobile phase, what is moving and what is not moving. Those are the kind of things they like to ask you. The principles, the basic principles surrounding the different type of chromatography. Okay. So in the mass spec of A-level content, you see this is much later on in the A-level content because they are more complicated, because it's about molecule. See how the mass spec of Br2, which is a molecule, is not just for the molecule. Okay, so that thing, the lowest one, is actually M plus. They don't give you the axis, but it's actually mass of a charge, or sometimes they put it M over Z, and then it's percentage abundance or relative abundance or whatever similar kind of thing that talk to you about abundance on the y-axis. Okay, so that's M. That is M plus 2. The whole thing has a plus 1 charge. That thing is M plus 4. The whole thing have a plus 1 charge. Notice the ratio is about 1 to 2 is to 1. And notice that there's actually 2 lines there. Okay, it's about 1 to 1 there. And there's actually just bromine 79. And there's just bromine 81. So bromine 79 and bromine 81 are roughly present in 1 to 1 ratio. They are not exactly 1 to 1. That's why you get 79.9 as your relative atomic mass, which means there is just slightly more of the bromine 79 than bromine 81. But for simplicity, we can think of them as 1:1. When you have your first bromine atom, it can be 79 or 81. When you have your second one, it can be paired out as 79, or it can be paired out as 81. So I'm doing like a probability kind of diagram. Okay, so your first combination will be 79Br. Don't forget, plus. Your second combination and your third combination would overlap with each other because they will be 79Br, 81Br, which is the same as 81Br, 79Br, because when you add up the mass, they overlap at the same region. Sorry, there's not a plus. Okay, so each of these will be positively charged as a result of what happened in the mass spec due to this process, which I won't elaborate here for Cambridge International, but it has to be charged. If the bottom bit is not charged, you won't see anything at all. Okay, so this is a simple molecule. This is more complicated because it's a more complicated molecule. So you get M plus, you get M plus 2, plus, you get M plus 4, plus. This gives you the one line. This gives you two lines. Well, exactly not two lines, but it's double the intensity because you have both of them contributing to you. That's why it's 1:1 ratio. You can do the same for your chlorine, where you have 35 chlorine and 37 chlorine. But 35 chlorine and 37 chlorine are in the ratio of 3:1, not 1:1. The concept similarly applies, okay? And therefore you'll be seeing, I think it's 9:6:1 if I'm not mistaken. You can work that out with your own probability diagram based on what I've just told you, alright? But in total you see 5 lines. You don't see 3 lines in the mass spec of Br2 molecule, you see 5 lines altogether. You see more lines here because they are more complicated, bigger molecule. That is the parent ion. That will be the M plus, which is essentially C2H5Cl plus. And you can think about the small one, that is like 3:1. And that is because that is with 35 chlorine. This is M plus 2 plus, that is C2H537Cl plus. That is your M plus 2 because 37 chlorine. Okay? We can next talk about chromatography a little bit. So that's what happened in a GC. Okay, gas chromatography. What happened inside? You vaporize it, you push it with the gas. Alright, so there's an oven. You push it with a carrier gas, an inert carrier gas like neon, like argon or hydrogen. Sorry, not neon, argon or hydrogen or etc. or nitrogen. And then they get pushed along. Depending on their property, they either stay in the column. Okay, they either stay in the column longer or they stay in the column shorter. And you will get something called retention time. That is on the x-axis. Alright, on the y-axis is your intensity or something like that, and then you work out the area under each portion. So there's area for that, area for that, area for that, area for that, area for that. So the percentage of this will be the area of this divided by the total area times 100%. That's something you will have done when you analyze a chromatogram, which is the result from a GC experiment. If you have a TLC, which stands for thin, T-H-I-N, thin layer chromatography. Okay, this is more like what we do in the lab on the day-to-day basis. This is a silica plate. It's made of SiO2, so that thing doesn't move. What moves is solvent. Your mobile phase is the solvent. Dependent on the property of this substance in the solvent, they will move out at a different rate, dependent on their solubility in the mobile phase, solubility in the solvent. The more soluble they are in the solvent, the further up they travel. The distance from the point, from the starting point, not from the line where you draw the thing, but from where you spotted it, yeah? Usually we will spot on the line, obviously, but sometimes we are careless. We might have spotted above the line, and it's from where the spot is, because it's where it starts to separate, to where you take it out before the solvent reaches the top. You have to take it out, there's the solvent front. So the RF is going to be that distance over that distance, and you can compare with the literature, where it gives you one dot or one color. That means it's pure and pure. This is a mixture, and this mixture contains this non-product because the RF value matches that, and something else which I don't know. Okay, but I can separate them. It does a structure determination. You can use analytical techniques like this. Separating mixture, they put KPC, which is to do with partition coefficient, in this analytical technique. In order to find questions on where I tackle partition coefficient, you can look up the topical playlist on ionic equilibrium. That is as part of A2 ionic equilibrium, A-level ionic equilibrium, with all the other equilibrium constant like Kc, Kw, Ka, etc, etc. Okay, so it's to do with solubility of a solute in one solvent relative to the other solvent, where both of these do not mix. They are what we call immiscible solvents. So you're doing extraction. You try to take out something that is more soluble in. Well, you try to take it out from one solvent to another solvent which is more soluble in. Okay, the calculations are quite commonly asked. You can find out a few examples in the ionic equilibrium topical playlist. All right. Finally, these two are the most important big concept in this analytical technique. Carbon-13 is quite new in the syllabus, but every single year since the introduction of the new syllabus, Carbon-13 has come up every single year in the paper 4. Okay, Proton NMR has been around in the A-level chemistry syllabus for a very, very long time, so there are far more examples from past year papers. But bear in mind that syllabus changes, so don't simply just do a lot of papers without understanding your curriculum. Yeah. TMS stands for tetramethyl, so there are 4 methyl. It's a silane, it's not a methane because it's a silicon. It's a tetrahedral silicon, 109 degree, because it's got 4 bond pair and 0 lone pair. We talk about VSEPR, you can have a look at my structure and bonding playlist. Okay, the 4 bond pair repel equally, giving you 109 degree there. We use TMS as our standard solvent, and that appears as 0.00 parts per million. That is your chemical shift, delta, chemical shift, 0.00 ppm. And that is not how Proton NMR looks like, because Proton NMR increases that way. The delta increases that way. So I find it weird that they have the axis there, yeah, okay? But you can have a single line. That single line represents, so here you have one environment, another environment, 3:2:1. That is the number of proton. But the environment, this CH3 is different from this CH2, it's different from this OH. So that is your, if I label it A, B, and C, that will make your life easier. So that will be C because it's singlet. It talk about its coupling to how many neighboring protons, but because it's an OH, it doesn't couple through the OH at all, so it just appears as singlet. Because the OH there is it doesn't anything proton to the OH, it doesn't get coupled. So this proton here, they don't couple to this. What they see is they see these 3 neighboring proton. You got 2 on yourself when you are here. Therefore, when you are here, 2 of these are the same. You see 3 neighboring protons that you couple to. Therefore, you give 3 plus 1 line, so they give you 4 line, which is a quartet, and that is environment B. Where you are at, where are you? Okay, you are here, therefore you see 3 neighboring protons. You're also next to oxygen, that's why the value will be somewhere between 3 to 4. Okay, whereas this one will be A. When you are here, there are 3 of you, 3 protons, but you see 2 neighboring proton, so 2 plus 1 give you 3 lines, which is the 1:2:1 triplet. This is 1:3:3:1, which you have learned as part of Pascal triangle for the splitting intensity anyway. Okay, something they don't mention there is the use of CdCO3 is a deuterated solvent. We use it as a solvent to dissolve our compound in. Okay, is deuterated because we do not want to introduce extra proton to our NMR, so that this deuterium, they won't show up as extra proton in your proton NMR, because you only want to see the proton, the hydrogen, which is the proton for your compound. Deuterium is 2,1, is actually the same as 2H1. So deuterium is actually that. It's also hydrogen, but it's not just one proton, it's got one proton and one neutron. That's why when we talk about proton NMR, we refer to proton. That is just a proton because there's no neutron. We use that as a solvent, deuterated solvent. We use this as a standard. We don't always put this in our compound, obviously. We put this in our compound as a solvent. This is something to calibrate the spectrometer. Just like how we can, I haven't finished actually. There's something else they don't mention there, which is to do with labile proton. This is like the last thing in the proton NMR. We talk about OH bond and NH bond being labile, Labile. So you can add D2O, that will disappear. That means you will see one lesser signal due to the labile proton. This was OH, this is OH. So this peak will disappear if you add D2O to this compound, because D2O plus an alcohol. So here you got proton. So if they exist in equilibrium and they give you that, so when they give you that, there is no more proton on the original species due to the what we call fast exchange. Okay, fast exchange is a result of labile proton. Whether you have OH or NH, they will disappear. If you add D2O, you will get 2 signal instead of 3 signal. Okay, just like how we work out symmetry for proton NMR, here carbon-13 NMR is much simpler. Work out the chemically, we call them chemically different carbon. Okay, this is a symmetrical compound because I hope you can see there's a mirror plane there. So what happened is, that is, sorry, I should probably use a brighter color. I will use a brighter color. That in the middle is one carbon. Another one, I use a different color actually, red. This is a different carbon, but this is also red because they are symmetrical. Okay, so there are 2 of them giving you the red one, and then another one will be the last one. This and this carbon are the same. Excuse me. So that and that carbon are the same. Okay, so you see how these are higher intensity. So again, that is to do with chemical shift. They increases from right to left. Yeah. So this is the one with 1 carbon. If I label that red one as B, that pink one as C, environment C, that will be C. In terms of whether you are the blue one, which let me label that A, the further you are away, I would imagine this would be A, and this could be your B. Okay, it's quite hard to tell whether this is A or B, but the one with the lowest intensity will be the one with 1 carbon, whereas the rest, they have 2 carbon, they overlap onto each other. Okay, there's something else which is not mentioned in this analysis. It's actually from your AS chemistry. It's to do with infrared. Okay, so although they are in AS, they are from AS, you cover this in AS chemistry, it tells you the bond. They don't tell you functional group, they tell you the bond. Okay, usually we look for the broad strong absorption of OH, and we look for the carbonyl, that's around the 1700 or 1800. However, you also need to look out for other stuff. So other stuff meaning some stuff, example, you look for carbon-carbon or CH or CO of an ester. So those things are all given in the data booklet, so you can refer to them based on the information given or based on the structure that you have been given. The reason why I include infrared here is because infrared is part of analytical technique. I put infrared in my topical playlist, both in the AS carboxylic acid and its derivative playlist, as well as in this A2 A-level chemistry playlist on analytical technique, because it's for AS. That means they could ask you in A-level paper 4 if they want to as well. Okay, this is the end of this 10 video series on these infographics provided by the Cambridge International Examination Body. By no means are these completely your syllabus and specification from Cambridge International. For that, you have to refer to the actual document which outlines every single learning objective that you have to master that they can ask you. Okay, anything that's in the syllabus, they could ask you. Do not try and predict questions. Try to cover as many concepts as you can. Go through my topical playlist where I outline and explain how to address the questions. All right, but by no means, I guess when it's close to exam, it's more important to learn how to tackle questions and what not to do, rather than focusing on the what, because that's something you should have done all along while you are revising. Okay, thank you for following this 10 video series. Please do check out other great contents on my channel. So catering for 14 to 18 years old, people who are doing GCSE or O-level or A-level chemistry. Full paper tutorials as well as topical playlists are available. So navigate around the channel and I hope you find what you want, and share them widely with your friends, your group chat, your juniors if you are leaving school, your seniors if you're still in school, I guess, relative, whoever else you think can benefit from this channel. Okay, so thank you for watching.